In this question, I and j are horizontal unit vectors. So what that is saying is it's like we're on a table. Here's our particle, and I is going in this direction and j in this direction. It's not like j is going up vertically from the table, which is quite often use j as like the y-axis or something. It's horizontal, and then it would be sort of k that would be going out of the table. We don't have to worry about that because we're only moving in 2 dimensions. Yes, there's going to be a weight. Also, that's going to be a force, but it's going to be balanced by normal reactions. So we only have to consider these two forces on the particle. Let's find the resultant force then. Resultant force is just going to be the two of them added together. So 4 minus 1, I'm going to write it in vector form, plus lambda mu, which gives lambda plus 4 and mu minus 1. Then we're told that the particle moves in the direction of 3i plus j, or 3, 1. There is constant acceleration here because the force is constant. So I did it slightly differently to the mark scheme. I went and used F equals ma, and I said that lambda plus 4 mu minus 1 is equal to 4. Now it's not equal to 4 times a. The acceleration is just in this direction. So it's going to be 4 times 3k and k. The acceleration is going to be some multiple of 3, 1. So I've written it as 3k and k. And then I can construct some simultaneous equations. So 12k is going to equal lambda plus 4, and 4k is going to be mu minus 1, which means if I multiply this one through by 3, then 12k is going to be 3 mu minus 3. We can now set these equal. They're both 12k, so lambda plus 4 is equal to 3 mu minus 3. That means lambda minus 3 mu plus 7 is equal to 0. If you don't like me using k, you can use ratio instead, which is along the same lines, because with ratio you just have a scalar factor. But you could say, I mean, you're kind of using the idea of gradient, I guess, but yeah, lambda plus 4 over mu minus 1, the top divided by the bottom, must equal 3 divided by 1. And you get there slightly quicker to here. Okay, but I quite like, personally, I think it makes a bit more sense to say it's some multiple of 3, 1 and go from there. Anyway, we're there with our equation. We're then told that lambda is going to equal 2. So let's work out what mu is. It's going to be 9 minus 3 mu, because I've just done 2 plus 7 equals 0. So that means mu is going to equal 3. And that means we've got our force. Okay, put it back in. It's going to be 2 plus 4 to give us 6, and 3 minus 1 to give us 2. And now I can find the acceleration. So 6, 2 is going to equal 4a. A is then going to be 1.5, 0.5. Okay, that's all the force stuff done. It's just to smooth that now. 2 dimensions. We've worked out this acceleration. We're told at time t equals 4, it passes through the point B, whereas it was at the point, I think it was at the point A at the very beginning. So t equals 4, and now we want to know its displacement basically from its original starting point. We're also told that it was at rest. It says it somewhere, I think. There we go. It's at rest, and then these forces are applied. So U is equal to 0, 0. So S equals UT plus a half AT squared. Actually, U is just 0, so it's just a half AT squared. T squared is 16 times by a half is 8. So it's 8 times 1.5, 0.5, which gives 12, 4. That's the displacement, but we're asked for the length. So we just use Pythagoras. We're going along 12, up 4, 4 squared plus 12 squared, square rooted, which gives root 160. That's the exact length. I tend to feel in mechanics we're dealing with, models and so forth. So I'm writing it to 3 significant figures, 12.6 meters. Well done.